All right, we're back for part 2 of our review for the Chapter 3 test. And we're continuing our discussion on vectors. And what we want to do now is talk about components. So, well, let me draw for you a coordinate axis. Make a nice, neat one here. All right. Good enough. Close enough, as they say. So if I draw a vector, and let's say this is my x and this is my y, and I draw myself a vector going in that direction, and I call this vector, let's call this vector, let's say it's 5. I'm going to give it a magnitude of 5, and I'm going to say it's going at 20 degrees to the x-axis. My question to you is, what is the x component of this vector? Now remember, you can take any vector at all and break each vector up. You could take any vector and break it up into two perpendicular components. One in the x direction, one in the y direction. And we call those components of the vector as follows. Well, first thing we want to do is let us draw a little box down and over. And you got to make sure when you draw that box, you're at the tip of that arrow. That is so important to be accurate with that, because now this vector right here is going to be my x component. And this vector right here is going to be the y component vector of the 5 vector. So here, this one here, right there, this is my x component. X component. And that x component is going to be the magnitude of the 5 vector, which is 5, times the cosine of 20 degrees. That's the x component. The y component here, this guy here is going to be the y component. And the y component is going to be 5 then times the sine of 20 degrees. And that is because if we look at what we've got 5 going this way, and we're saying this 5 we're going to split up into two pieces. One piece going this way, and one piece going this way, and this y component here and this x component here are going to add up to give me this vector here. And this whole thing's at 20 degrees. And if we look at this and we draw a rectangle, then this y piece over here is the exact same piece over here, right? And we know that the cosine of this angle, 20 degrees, is going to be the adjacent, which is x, over the hypotenuse. Well, here's my right triangle right here. That's the hypotenuse. This is the two legs. This is a right angle right there. So adjacent, this is the adjacent side, is going to be x over the hypotenuse, which is 5. The sine of 20 degrees is going to be the opposite side, which is y, because here's 20 degrees. The opposite is going to be this piece right here, which is going to be y, over the hypotenuse again, which is 5. And now you see what happens is if we multiply both sides of this equation by 5, we will get x is equal to 5 times the cosine of 20. And if we multiply both sides of this equation by 5, then this will cancel. And you'll get y is going to be equal to 5 times the sine of 20, which is what we said right here. The x component is 5 cos 20. The y component is 5 sine 20. So if you're given this with some kind of a vector here, all right, and let's call this vector, let's say this is vector D, and this is angle theta. The x component is going to be d times the cosine of theta. And the y component is going to be d times the sine of theta. That's something that you need to know and get down. All right, the other thing that we're going to talk about doing today is talk a little bit about projectile motion. Projectile motion now simply has to do with something in the air without having any power behind it. It's just flying through the air in both an x direction and a y direction. So if I draw some kind of an axis here, something that's in the air moving, and it's moving like a parabola, and it's got some x direction motion to it and some y direction, and there's nothing powering it other than gravity pulling it down. That's a projectile, and that's projectile motion. So a rocket ship that's taking off, right, is not a projectile. Why? Because the rocket has its own power here, and it's giving a thrust or a force which is propelling it along. A projectile has nothing propelling it along. A tennis ball, as it's going through the air, is a projectile, because there's no rocket thrust on a tennis ball. It simply is by itself. It's just under the influence of gravity pulling it down. So in order for something to be a projectile, it has to be by itself. So like a baseball or a tennis ball or a bullet being fired, these are all projectile motions. An airplane taking off or a space shuttle being launched is not an example of a projectile. So we need to know and understand that as well. The other thing that we need to talk about in projectile motion is if we, and let me just quickly clear this and get another page up here for us. If I want to describe something in motion that's going like this, maybe something that's coming off of a building. So let's say this is a building here, and something's launched right there with some velocity v. And let's say it's a ball, and it's heading like this, and then it's heading down. The velocity, when I just say velocity, I mean the combined velocity. I don't mean any particular x component or y component. If I say the x component of the velocity, you'll know exactly what I'm talking about. But if I say velocity, I'm talking about the total combination of both the x and y components at any point. So if I want to talk about that, where would the magnitude of the velocity be the smallest on this kind of a trip? Let's say something's fired out here. Well, let's take a look at it. If we fire it out of a cannon right at this point here. At this point here, you see this is the velocity. It's got an x component and it's got a y component. Over here, it's got an x component and a y component upward. Over here, it simply has an x component, and I'm going to designate the velocity in the x like that. There's no component in the y direction at this point because it's at the top of the trip. Over here, we got an x component because it's still moving in the x direction, and at the same time, it's moving down in the y. And over here, it's got, this is x by the way, it's got a velocity in the x, and it's still moving in the x direction, and it's moving faster down as it's going downward. So if you want to know where the magnitude of the velocity is the smallest, it's going to be right here at the top. Because right here at the top, you only have an x component. You don't have any y component to add to it. So since we know with a projectile, the velocity in the x direction is exactly the same through the whole trip, doesn't change from start to finish, then what's going to make or break the velocity as far as what's the greatest speed is going to be the y component. So where the y component is the largest, that's where it's going to be the fastest. So it's going to be the slowest right there, slowest, because it has no velocity in the y or vertical direction. It's going to be the fastest here, fastest. Why? Because this is where this, sorry about this, this is where the y component is the largest. Because on its way down, it's going to be increasing in velocity due to gravity. Gravity's accelerating it, remember it, so it's going to be largest here, it's going to be the smallest over here. What happens when it's about level? Then the velocity that it had right here at the start is going to be the same right here, right where it's level. Why is that? Well, we know that the x components are the same, so this one that I'm going to put in a box and this component here are going to be the same. How about the y component? This y component here is going to be in magnitude now the same as this one. Why? Because you're at the same level. You're at the same level. And anytime we have something at the same level, if you have a y component here, Vy, and let's say we have an x component here, Vx, and it makes this trip and it comes back down to the ground at the same location, then you're going to have the exact same Vx here, and you're going to have the exact same magnitude of Vy here, except it's going to be going downward. So if this is equal to plus 5 meters per second here at the start, at the same level, this is going to be minus 5 meters per second. Minus because it's going down, but the magnitude is going to be 5, and the magnitude is going to be 5. So magnitude-wise, the velocities, magnitude-wise, at these 2 points, there and there, are going to be identical. Okay, so what we're going to do now in part 3 is and part 3 and part 4, we're going to solve 2 or 3 important problems that you need to know how to step through. We're going to solve them together. It gives you a little practice, and hopefully you'll be set for the test. So we'll see you in part 3.